All right, so as promised, we're back to some Python to actually look into how we want to do this power matrix object. So to kind of remind us where we're at, we have this kind of dictionary representation of our graph. So it's going to be stored as a D. I then have a couple nice little printouts saying how many vertices and edges and things like that. I'm then going to immediately compute that adjacency matrix version of that, which is then going to be this big 10 by 10 thing that's littered with zeros and ones. We don't have any directionality to worry about. So we have some symmetries going on, and that's going to be our starting place. So we have this big old matrix of zeros and ones. If you want to, you can always just start with that. Basically, anytime you're given a graph, just assume that it's stored as an adjacency matrix, and then you wouldn't need this first step. I tend to like to store them as dictionaries and then convert the adjacency just because this is a little bit easier for me to kind of design. So when it comes to constructing homework problems, I'm like, I want this thing to be connected to here and here and here. But however you want to design it is totally up to you. All right, so when it comes to my power matrix function, so I'm stealing the term like the power mod function. So I'm going to call it power matrix. It's going to eat my base A, so the thing that needs to have the power raised to it. And then R is then going to be the exponent. So in the example, we were looking at 83. And then from here, we're going to then go through that little kind of constant update cycle over and over and over again. So I'm going to initialize the little a as being my matrix A. N's then going to become the length of that thing, so kind of how many rows or how many columns that thing's going to have. The only reason I need that is because I have to construct this cute little identity matrix. So there's a variety of different ways you can compute this. So this is going to be a big 10 by 10 matrix that just has ones down the diagonal. So the diagonal is where those two indices match up. So if the I is equal to the J. So I kind of was I don't know, lazy in this scenario in that I'm going to go through basically all of the n's, so the length of my A. So it's going to be this nested for loop for both of those. And I'm going to compare if the indices are the same. So if the I and the J or the X and the Y are equal, well, that would kick out the Boolean of true. And then I convert that Boolean of true into an actual honest to goodness number. So that's going to be stored as a 1. If I'm off the diagonal, then it's going to kick out a false, which then that would obviously return a 0. So it's a dumb way to compute this little identity matrix, but it does require us to kind of have that initialization of what this B is going to be. So the B is going to be constantly updated to actually create the A to the 83rd. So it's essentially going to be a 1, and then it's going to turn into an A, and then I'm going to multiply in the A squared, and then I'm going to multiply in the A to the 16th, and then I'm going to multiply in the A to the 64th. So it's going to be updated a few times. Whether or not it gets updated is then going to be dependent upon whether or not it's part of my recipe. So if it's a needed term, so I'm going to take the R, reduce it modulo 2, and if it kicks out a 1, so 83 reduced mod 2, kicks out a remainder of 1, which is going to say I need that first term. So the B is going to be updated, so it's going to be multiplied by whatever is currently stored as the A. So initially, it would be that 1 multiplied by the A, which is then just going to be stored as A. Then I'm going to update my A by converting A into A squared by taking A times A and then restoring that as A. Then I'm going to take the R and divide it by 2. So the 83 is going to go down to a 41, and then we're going to go back up into the start of this. 41 mod 2 is obviously going to kick out a remainder of 1, which is telling me that the number 83 has a 2 in it. So I would then have to take my A and now multiply it by my A squared to create the A cubed, and then rinse and repeat that over and over and over and over again. So it's a pretty tidy little while loop. There's a little bit of meat to it to kind of make sure it all works. But at the end of the day, it's just one simple while loop that's going to run as long as this R is not zeroed out. Every single time, though, the R is going to be chopped in half. So that's where that log base 2 structure is then going to come into play. So if you give me an exponent of 83, it's going to run in log base 2 of 83-ish number of loops. So it's going to create this nice little product. It's going to obviously make use of the matrix multiply function that we had before and allow us to make these things to really, really, really big powers. So the example that we had to make sure that 83 works, I guess we should probably make it a 3. Since we know what 3 is supposed to do, let's make sure it actually works. So if I do that, the number of paths of length 3 from 0 to 0, well, that is definitely 0 because that's what it was supposed to be before. If I do it with a 2, that one should kick out 3, I think, which it does. So the example we had was what, 83 So we printed off that. So there were that many. Again, realize that that is actually one entry of this kind of 100 by 100 array. So if I printed out the whole terrible thing, break some things. Obviously, there's a ton of stuff going on there. So there's 100 numbers that are all right around 47 digits long. If I comment that thing out, you can obviously, take sky's the limit for how many powers you want. So if I want paths of length 1,000, sure. 576 decimal digits long, whatever that number happens to be. If I want paths of length 10,000, which is again absolutely ludicrous to think about because we have a network that only has 10 nodes. So why would I want a path of 10,000? I don't know, but we can, so we might as well try. So if we run it with 10,000, uh-oh, we might have broken it. Now we get to play with Python and not care about, lengths of things. So that's the number of paths. So good luck counting that explicitly. And that particular number has 5,761 digits, or if you converted it into binary, it would have just under 20,000 bits. I don't really want to push any farther. Maybe I do. All right, let's go up to 100,000. If I didn't run this through, the internet and actually ran it locally, this would be done immediately. But here we are. We're playing with it just because it makes sharing things really nice. So we'll let that kind of think. Well, while that thinks, I'm actually going to jump back to the notes just to make one or two last little comments about this particular section. So let me actually share back to my iPad. So while we were going through all of these things, we had kind of the general question that this kind of question of adjacency matrices and powers of these things are going to give you abilities to count the number of paths. The unfortunate thing in this is that it has this idea that it is counting explicitly, paths of a set length. So if I want paths of length 3, it doesn't allow me to sit still potentially or to, get there and then pause. So if I wanted to allow paths of length up to 3, what I have to do is I have to actually add in some abilities to sit still. It's going to increase the number of paths fairly dramatically because we're going to have lots of extra little loops and things like that, but it's an easy enough fix to do. So what we do is we go back to our original graph and we add little loops on every single vertex. And if you think back to this kind of identity matrix that we just generated, that actually is going to then be the thing that we add to it. So the identity matrix is really just a graph that has single dots with loops on themselves. If I gave you that as an adjacency matrix and then said, okay, generate the corresponding graph, it would just look like 1, 2, 3, 4 dots with little loops on it. Well, if I add that thing into the matrix A, all it's going to do is it's going to take that column or that diagonal that was all zeros before, and now it converts it into a diagonal of all ones. So once I have that, I can do all of the same games that we did before. Basically begin raising this thing to larger and larger powers. So if I took this 1 plus a and raised it to the third, that would start looking at paths of length at most 3. Not length 4, but it had paths of length 0, 1, 2, and 3 all incorporated for it. We won't spend a ton of time on that, but it's a cute little one-off that you could easily accommodate various other scenarios in that you just add on those extra little things if you need. So it's there. There's a couple extra little cute games that you can play. So in our graph G, you can obviously raise it to larger and larger powers. Eventually, this graph over on the right has no zeros in it. The moment you no longer have zeros, you obviously know that everything can be reached in a certain number of moves. In this, nice little connected graph, obviously, if I have 4 vertices, the hope is that I can get everywhere in at most 3 moves. In my graph that had, let's say, 10 vertices, wherever it happened to be, the hope is that I could possibly get to everything within 9 moves. So again, the kind of silliness that we had before of like, here's 10 vertices, where can I get in 100,000 clicks is super duper overkill, but it's still kind of a fun question to look at. So if you want to, you can take a peek farther into the notes. I have a little bit of extra stuff about that, not a ton more, but it's there for your perusing. I did see that my bit finished, so I'm going to swap back to it. So if I swap my screen back into my Safari page, if I go back to my graph with with only 10 vertices, if I wanted to count the number of paths of length 100,000, well, there are that many paths of length 100,000 that start at 0 and end at 0. So that number is 57,000 decimal digits long. And if you converted it into binary, it would in fact have just under 200,000 bits. So it's a big old number. And obviously you would not want to compute that by hand, and that would take obviously the rest of your life times a ton. And you can see that it's really easy to compute here. So hooray, even though it's a not very efficient program in that it's got triple nested for loops and things like that, it does execute very, very quickly. And that's kind of the little game we're going to play a whole bunch more as we move forward, is that we'll take some kind of cute little tasks, chat about how we can actually implement them, and kind of dwell on some of those runtime questions a little bit more. So hopefully some of this is a little bit of review, maybe a little bit of poking into some new stuff. We'll keep this game going and have a lot of fun doing it. So enjoy.